Okay, so now what we have here is the algebra of events. So combine two or more events by using the analogous set notations. So now let's say that as a review, I'm going to go into some other page over here. So let me go 48. And okay, so let A, B, and C be events associated with an experiment whose sample space is S. So now let A, B, and C be events associated with an experiment whose sample space is S. Whose sample space is S. Now the complementary event, there is something called number one, the complementary event. Okay, and what that is for every event A, there corresponds another event A prime called the complementary event to A, which is the same thing that we use in sets, at least so far. Let me not jump into any sort of conclusions. So it says that for every event A, there corresponds another event A prime, called the complementary event to A, called the complementary event to A. It is also called the event not A. It is also called, so that's basically what we were looking for. It's also called the event not A. Not A. So for example, if you take the experiment of tossing 3 coins, an associated sample space would be, so for example, for tossing the experiment of tossing 3 coins, the sample space would be basically HHH, would be HHT, would be HTH, would be THH, would be HTT, would be THT, would be TTH, would be TTH, and also TTT. So you have 1, 2, 3, 4, 5, 6, 7, and 8 outcomes here for tossing 3 coins. Now let A be equal to the basically HTH and HHT and THH. Be the event only one tail appears. Only one tail appears. So only one tail appears. You can see one tail here, one tail's here, and one tail's here. Now, clearly for the outcome HTT, the event for the outcome HTT, the event has not occurred, but we may say that the event not A has occurred. So here we can say that for the outcome, for example, for the outcome HTT, the event has not occurred, but the event not A has occurred, thus with every outcome which is not in A, we say not A occurs. Thus with every outcome which is not in A, with every outcome which is not in A, we say that not A occurs. We say that not A occurs. And that's, now I will talk about sets as well, and there you will also find basically things that I mean, in the sets we do the exact same thing. I don't suppose they are two different things. They are just using different words to basically talk about the same concept in the context of probability. Otherwise it seems to be the same thing. But let's read on to see if I'm not wrong. Okay, so thus the complementary event not A, so thus you can say that thus the complementary event not A to the event A, is A prime, you can say, which is the same thing as basically not A. Okay, that is equal to basically in this case, so basically our S was basically this whole all of these outcomes here, and this is not A. So that means that over there we said that basically with every outcome which is not in A, we say that not A occurs. So not A occurs for every outcome which is not in A. So for example, this outcome HTH is in A. HHT is already in A, or THH is already in A. So the rest of these outcomes would belong to A prime or not A, basically, meaning that HHH or HTT or THT or TTH or TTT, these would be basically not A. These would be not A. Or you can say that A prime is the same thing as omega, such that omega belongs to S, omega belongs to S and omega does not belong to A, right? Which is, by the way, the same thing as S minus A, meaning that all the members that you find in S and minus the members that you find in find in A, meaning that meaning that suppose that for example you have suppose that for example this is your S and this is your A, this is your S and this is your A, and A is supposed to be a subset of S is supposed to be a subset of, I'm sorry, A is supposed to be a subset of A. So this is not a good way of drawing this thing, meaning that I have to, well, take this as, for example, S as my universal set, and A would be, for example, I have all of these outcomes over here, and some of these outcomes are related to A. Now, of course, S minus A would be, for example, let's say, for example, S1, S2, S3, S4, S5, S6, S7, and S8 you have here. So what that means is that S would be equal to S1, S2, S3, S4, S5, S6 through S8. S1, S2 through S8. Right? That would be S. Now S minus A is equal to all of the members of S except for the members of A, which is S1, S2, S7 and S8. S7 and S8. And that is S minus A. Now A prime, or which is the same thing as not A, is basically all the members of S except for the members of A, which would be S1, would be S2, would be S7, and would be S8, and which is by the way equal to S minus A. So that means that then S minus A is the same thing as A prime, right? So that's basically that. So that is, so far we have no problems. Now, the next thing that we have is the event A or B. Is the event A or B, which is basically, you know that the union of two sets A and B, denoted by basically A union B, contains all those elements which are either in A or in B or in both, meaning that for example, suppose that this is for example two sets over here. Let's call this set A and set B, and here you have A1, A2, A3, and B1, B2, and B3. And so A union B would be this set A1, A2, A3, and B1, B2, and B3. B1, B2, and B3, right? This is a union B, which I can basically in English, I can say basically all those elements which are either in A or in B or in both. So all the elements that that are either in A or in B or in both. Okay, so that's basically the union of two sets. Now, when the sets A and B are two events associated with a sample space, then A union B is the event either A or B or both. This event A union B is also called A or B. So this is when we get to basically when the sets A and B, when the sets A and B are two events associated with the sample space, are two events associated with a sample space, then A union B is the event either A or B or both. And this event A union B is also called A or B. Therefore, event A or B is the same thing as A union B, which is the same thing as omega, such that omega belongs to A or omega belongs to B. So now, to make sense of this situation, of course you need to learn this definition and all of this, basically all of the terminology here, but still you do need to understand it this way. Otherwise, basically the word or, for example, might confuse you, right? So what that means is that, for example, the event A or B, so if I have, for example, my A over here and B over here, and again, so let's say that this is A, this is B, and I have A1 over here, A2 over here, A3 over here, B1 and B2 and B3, for example, then A union B would be A1, would be A2, would be A3, would be B1, would be B2, would be B3, which I can write as basically, well, the same thing. A union B is equal to omega, such that omega belongs to A or omega belongs to B. So I'm using the word or here, but at the end of the day, that's going to be what you will get, right? So remember that A or B has to do with the union of the two sets, meaning that is A union B, right? I mean, it's kind of, I mean, at least to my mind, it's counterintuitive. It doesn't make much sense, but that's how, for example, the word or is used in mathematics, and you need to use it in the exact same way. Otherwise, of course, it doesn't fit with the other fit with the other parts of mathematics. And there is also another event called the event A and B. there is also another event called the event A and B. Okay, so now the next thing that we have here is basically the event. So we talked about the event A or B. Now there is something else called the event A and B. So the event A and B. A and B. So basically the event A and B, this is again a little bit counterintuitive, meaning that, for example, at this my mind or my brain links and to basically it links and to union. It links or to, well, not exactly to intersection, but kind of. So right now it's kind of confused. So I need to help my mind, my brain to actually get itself somehow around these issues, right? So what that means is that now the event A and B, so now you know that basically again, if you have these Venn diagram and this basically a set over here, for example, these two sets over here, let's call this A and let's call this B, and A1, for example, A2, A3, and B1, B2, and B3. So then you know that over here, A intersection B, that would be basically all the members that are common between all the elements that are common to A and B, which is basically A3 and B3. That is A intersection B. And in simple English, I can say that that the intersection of two sets A intersection B is the set of those elements. This I can call the set of those elements. The set of those elements which are common to both A and B. Which are common to both A and B. That is, which belong to both A and B. That is, which belong to both A and B. Right? So that is A intersection B. Now, if A and B are two events, if A and B are two events, then the set A intersection B denotes the event A and B. Then the set A intersection B denotes the event A and B. So basically, if A and B are two events, then the set A intersection B denotes the event A and B. Thus you can say that A intersection B is the same thing as omega, such that omega belongs to A and omega belongs to B, right? So what that means is that, for example, For example, in the experiment of throwing a dice twice, in the experiment of throwing a dice twice, let A be the event score on the first throw is 6. So let A be the event score on the first throw is 6, and B is the event, sum of two scores is at least 11. Sum of the two scores is at least 11. Then basically what happens is that then you can write A as the score on the first throw is 6. That means that you will get 6, 1, for example. You will get 6, 2. You will get 6, 3. You will get 6, 4. You will get 6, 5. And you will get 6, 6. That is for A. And then the sum of the two scores is at least 11. So the sum of the two scores is at least 11. Then you would basically, if you're throwing basically a dice twice. So let's say that let's take this as 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and 6. Then you'll get 1, 1 through 1, 6. And then this is 6, 1 through 6, 6. And at least 11. So the sum of the two scores is at least 11. That would be, so all the way up to here, you have nothing here. 2, 6 is 2, 6 would be 2 plus 6 is 8, so still nothing here. So 3, 6 is 9, still nothing here. 4, 6 is 10, still nothing here. And 5, 6 is equal to 11. So you can start with 5, 6, and then again 6, 1 would be 1, and 6, 4 is 10. 6, 5 over here is again another favorable basically outcome, and 6, 6 is 12. So you have these three outcomes favorable to that event. So then you can say that B is equal to 5, 6, 6, 5, and 6, 6. So then in that case, you can say that A intersection B is equal to 6, 6. Then you have 6, 5, and then you have that's it basically. So note that the set A intersection B, which contains these two elements, may represent the event. So this set may, or you could say may is a good word to use here, may represent the event. The score on the first throw is 6. The score on the first throw is 6. is 6, and the sum of the scores is at least 11. And the sum of the scores is at least 11. So what that means is that based on this example, you can see that basically, as we said here, the event A and B basically is the same thing as so you can call this the event A and B, meaning that basically you're taking actually the intersection of A and B, which actually does make sense, because when you say the event A and B, you're taking the intersection of A and B, meaning that all of these omegas belong to A and also belong to B. So that makes sense. But on the other hand, in the case of A or B, in the case of A or B, we took the union of the two sets, A union B, which means that basically omega basically belongs to A, or omega belongs to B, and that is basically meaning that omega can belong to A or belong to B. In any case, basically that would be A or B, right? So that's basically what we have so far. Now, we have another thing called the event A but not B. A but not B, which is basically, we know that A minus B is the set of all those elements, is the set of all those elements which are in A but not in B. Therefore, the set A minus B may denote the event A but not B. Therefore, the set A minus B may denote the event A but not B. Okay. So, and also there was something that we discussed before as well, which is A minus B is the same thing as A intersection with B prime, which means that, let's say that I have some S over here, and let's say that this is my S, and I have some event A and some event B. Now we will have to take care of this later in some, let's take a look at this in some example. I cannot give you an example right now, but we will take a look at this. A minus B is equal to A intersection B prime. So let's see what that is. Okay, so now we seem to have everything that we need. So now we can go back to the example that we had and take a look at that. So we're just going to go back to the previous page, and there was somewhere over here. I can erase all of this and then come back over here to this example of 2 dice are thrown, and this was example number 6. This was example number 6. Okay, so now in the context of this problem, basically we said that we threw 2 dice. We threw 2 dice over here, and we got basically all of this sample space, and then we had all of these 3 A, B, and C events that were getting an even number on the first dice, which was all of these outcomes over here, and then the event B was getting an odd number on the first dice, which were all of these outcomes over here, and then basically event C was getting the sum of the numbers on the dice was less than or equal to 5, which was basically all of these outcomes here. And of course we don't need these anymore because we have already taken care of them all. Write this properly. Okay. Now we want to describe the events, for example, A prime. So A prime is basically all of these events that basically A was getting an even number on the first dice. So A prime, which is basically which you could call also not A, which is basically not A. We said that this is basically this would be all the elements of S except for the elements of A. And the definition here was so that was basically, this was called we studied this under the heading complementary event. Under the complementary event, and we said that A prime, you can also call it not A, and so for example we said that but we may say that even not A has occurred. So with every outcome which is not in A, we say that not A has occurred. So we said that with every outcome which is not in A, we say that basically not A has occurred. And so we said that basically A prime, which is equal to not A, is the same thing as basically omega such that omega belongs to S and omega does not belong to A. Omega does not belong to A, which is the same thing as S minus A, right? So what that means is that over here, what you need to do is that to find your basically the event A prime. So A is over here the event of getting an even number on the first dice. So that means that then you need to take all of the elements of S except for the elements of A. That means that this would be the event of A prime would be the event of getting basically an odd number on the first dice. An odd number on the first dice. Which is, by the way, equal to B. So that means that basically A prime is equal to B. So now if I go over here to the solutions, you can see that A prime is basically all of these elements, which is equal to B. Right? So that is basically the first one. Now, the second one is not B. So not B is the same thing as B prime, which means all the elements of S except for the elements of B. So B was basically the event of getting an odd number on the first dice. That means that B prime denotes basically the event of getting an even number on the first dice. Which is, by the way, equal to A. And so if you take a look at the solution here, we can see that not B is equal to A. Okay. So now the next thing that we have is A or B. So A or B, the event A or B is basically nothing but we said that basically A or B is basically basically nothing but A union B, which is basically omega such that omega belongs to A or omega belongs to B, right? So what that means is that now A is basically getting an even number on the first dice and B is getting an odd number on the first dice. So and all that we have over here is either even numbers or odd numbers, except for that there is nothing else that we have. So that means that if I have A or B, which is A union B, that means that I will get all of these elements over here plus all of these elements over here, which will in effect be basically which will in effect be A or B will in effect be equal to S, all of the elements of S. And if I take a look at the answer here, you can see that A or B is equal to A union B is equal to S. So that is basically the third part of this question. Now if I say A and B A and B. So we said that A and B is the same thing as A intersection B, which is the same thing as omega, such that omega belongs to A and omega belongs to B, meaning that omega has to belong to both A and B together, right? Meaning that, for example, if this is A and this is B, all of these elements over here are A intersection B. So that is basically the solution of A intersection B. So what that means is that I have to now basically the event A was getting an even number on the first dice, and B was getting an odd number on the first dice. So if I combine these two together with an intersection, of course there is nothing in common between these two sets. Between these two sets there is nothing in common. That means that in this particular case A and B, which is equal to A intersection B, is equal to the null set, which is what we can see over here as well. A and B is the same thing as A intersection B, which is equal to the null set. And then the next part of this question is A but not C. A but not C, which is basically all the elements of A except for the elements of C. I think this was which is the same thing as A minus C. So definition wise we said that this is A minus C, meaning that if this is A, for example, and if this is C, for example, then A minus C would be this part over here. A minus C would be this part over here, meaning that all the elements of A except for the elements of C. Now, in the context of this example, A basically denotes all the event of getting an even number on the first dice. C is the event of basically getting the sum of the numbers on the first dice less than or equal to 5. That means that I have to take all of these out. So of course basically all of these numbers that start with odd numbers is not going to be a problem because these are not in A anyway, meaning that 1, 1, through 1, 6 is not there, are not there. The only thing that we haven't so I have 3, 1, 3, 2, 4, 1. So basically I don't need to worry about these elements here because they start with odd numbers. So I have 2, 1, 2, 2, 2, 3, 2, 1, 2, 2, 2, 3. So these I need to take out from the set, and also basically I have to take out basically 3, 1, which is just simply not there because these are odd numbers, and 4, 1 here. So the only important parts are 2, 1, 2, 2, 2, 1, 2, 2, and 2, 3, and 4, 1. That means that if I take these elements out of this set, I will get basically A minus C. So, and of course we said that A but not C is the same thing as A minus C. Now let me see what the solution here is. So basically what I need to do here is just take these out of this set here, meaning that I can write this as for example A is equal A but not C, which is the same thing as A minus C, is the same thing as this set. 2, 1, 2, 2, 2, 3 is not there, so you start with 2, 4, and then 2, 5, and then you have 2, 6 as well, and then you have 4 as well, so 4, 1, you have 4, 2, you have 4, 3, all the way up to 4, 6, and then you have 6 as well, meaning that you have 6, 1, 6, 2, 6, 3, all the way up to 6, 6. That is basically A minus C, which is basically exactly the set that four, 2 is supposed to be taken out as well, of course. 4, 1, I'm sorry. 4, 1 has to be taken out as well. So I have to take this one as well. Just take this one out as well. So this is not there, but except for that, the answer is correct. So that is that. And the next part of this question is A but not C, then B or C. So if you have B or C is the same thing as B union with C. So B union with C would be the event of getting an odd number on the first dice, and the event of getting the sum of the numbers of the numbers on the dice. So over here you get 1, 1 all the way up to 1, 4. You will have to add these to this set. These are already there. So 1, 1 through 1, 4 you have to add. 1, 1 through 1, 4 you have to add. And these are already there. So you don't need to worry about these because these are already there. And you have to add these as well. This is also already there. So the only thing that you need to add is 3, 1, 3, 2. 3, 1 and 3, 2. So that means that then what was the question? B, C. Did I make a no, I'm sorry. No, I made a mistake, sorry. See, B or C, which is B union C. So this is B. This set over here, or this event over here is B, and this is C. So whatever there is not in B, which is in C, you have to add it to B to get B union C. Now over here I have 1, 1, 1, 2 through 1, 4. which is already there, because you have 1, 1 through 1, 6 already in here. Then you have over here 3, 1, 3, 2, and so on and so forth. So you have all the odd numbers here. So that means that these two I don't need to worry about. So that means that basically these I don't need to worry about, because these are odd numbers. These are even numbers, these 3 that I need to add. So I need to add 2, 1, I need to add 2, 2, and I need to add 2, 3. And also these two are already there, because this is all the odd numbers on the first dice. And then 4, 1 I also need to add. So that means that then you just basically B union C would be basically this whole set over here, plus these 4 elements. That's all that you need to do. And then we have, and then the last part of this question, and let me take a look at the solution here. That was part 7 of this question. That was B or C, so that was part 6 of this question, which is basically B union C, right? Now, the next part of the part 7 of this question, is B and C. So B and C is the same thing as B intersection C. Now, that means all the elements that are common between B and C. So you go all the way to basically 1, 1 through 1, 4, and all of these elements exist here. So these are common, right? So I have to write 1, 1 through 1, 4. These are already common. But these are not common because they start with basically with even numbers. So these are not there. These are again there, these two, but this is not there. So 3, 1, 3, 2. 3, 1 and 3, 2 is also there. So that is B and C, or B intersection C. That would be all of these elements here, right? So let's take a look at the solution. Part 7 of this question is B and C, which is B intersection C, is basically 1, 1. Let me bring this down so you can see the solution here. Is 1, 1, 1, 2, 1, 3, 1, 4, which is these elements up here. 3, 1, 3, 2. That is your answer. And then part 8 of this question. Part 8 of this question is A intersection B prime intersection C prime. So what that means is that basically B prime is the complement of B. C prime is the complement of C. So what that means is that so A is basically all of these numbers, all of these outcomes which have getting an even number on the first dice. Now B prime is basically getting an odd number on the first dice. So I'm sorry, B is getting an odd number on the first dice, when you get B prime, what that means is that you and of course you can write this as A intersection B prime intersection with C prime, right? Otherwise you couldn't simplify it, right? Or I think, if I'm not mistaken, you could also write it as A intersection B prime intersection C prime. I'm not sure about that. Let's check this, because I'm not really sure about this. This is called the commutative and commutative property of intersection and something like that. So we will check that out before moving any further. Okay, so I was actually looking for these, and I found this on Wikipedia. And as you can see, there is the fundamental properties of set algebra. There is something called the binary operations of set union and intersection satisfy many identities. Several of these identities or laws have well-established names. For example, this is called the commutative property, which is, well, that you could simply understand it, meaning there is nothing wrong, there is nothing difficult about that, meaning that, for example, A union B is the same thing as B union A, and A intersection B is the same thing as B intersection A. Then there is something called the associative property, which is basically A union B in parentheses union C is equal to A union B union C in parentheses, and also the intersection is the same way. And there is the distributive property, which is A union B intersection C is A union B intersection with A union A union C, and A intersection B union C is the same thing as A intersection B union A intersection C. And there is also the union and intersection of sets may be seen as analogous to the addition and multiplication of numbers. Like addition and multiplication, the operations of union and intersection are commutative, and associative and intersection distributes over union. However, unlike addition and multiplication, union also distributes over intersection. Okay. And two additional pairs of properties involve the special sets called the empty set phi and the universal set, U, together with the complement operator A of A superscript C denotes the complement of A. This can also be written as A prime. The empty set has no members, and the universe set has all possible members in particular context. So you have basically the identity A union, basically the null set is equal to A intersection with the universal set is of course A, and the complement is A union, the complement of A is equal to U, and A intersection the complement of A is equal to the empty set. So now let's take a look at these. Let's write them down once, and then we we will get out of here. Basically, we will take care of these, right? So the first thing that we have here is, I lost the page. The first thing that we have here is basically the commutative property. So we need to, the first thing that we need to tell, of course these of course must be and can be proved, but this, I mean, the proof of this has nothing to do with what we are doing here. So the commutative property, which is basically A union B, is the same thing as B union A, and A intersection B is the same thing as B intersection A. The associative property, is the same thing as A union B. Union C is the same thing as A union B union C. And also A intersection B whole intersection C is the same thing as A intersection B intersection C. And also there is the distributive property. There is the distributive property, which is basically A union B intersection C is the same thing as A union B intersection with A union C. And also A intersection B union C, A intersection with B union C is the same thing as A intersection B, A intersection B union with A intersection C. Now hopefully these do make intuitive sense, but of course, as I can remember, even when we were doing basically the algebra of sets, which was not here on YouTube, I basically, we did not prove any of these. Probably, I'm not really sure even if they're going to be proved in the next book. Probably, I don't know, in some university course or somewhere you might be required to prove this. Otherwise, I'm not really sure about that. Now there is also the union of A, with the null set, which is basically A. There is the intersection of A with the universal set, which is the same thing as so that is equal to A. And there is the union of A with the complement of A, which is the same thing as U. And there is the intersection of A with the complement of A, which is the null set, right? So these are basically the things that we needed. And now we can go back here and see what we had here. So we said that basically the question that we wanted to answer was A intersection B prime intersection C prime. So you can write it in based on what we read down there. You can write it either this way or this way. Now, basically, let's write it this way. And so A was basically A was basically D, so B prime is basically not B. And of course we established that not B, we established that B prime, which is basically nothing but not B, was equal to A. We already established that. So now A intersection with A intersection with A is of course equal to A, right? Meaning that suppose you have a set over here A, the intersection of A with itself is of course itself, right? So I can write this as therefore I can write this as A intersection with C prime. Now C prime over here is, I think we cannot simplify this any further, because this is getting the sum of the numbers on the dice less than or equal to 5. So that means that getting the sum of the numbers, if you're looking for C prime based on C, if C is getting the sum of the numbers on the dice less than or equal to 5, it has to be basically greater than 5. C prime would be getting the sum of the numbers on the dice greater than 5, which would be some elements, right? And then take the intersection of that with A, and that will give you basically whatever it is that you're looking for. So now let me see if they have actually provided an answer here. I'm not really sure if they have done so. So as you can see, this is A intersection with C prime, and you will get some elements over here, which is of course not that important to get the exact basically elements here. It's the only thing that is important is that you understand basically the procedure, otherwise the rest is just going through all of those elements and outcomes. Now there is one more question here which I think needs a little bit time, and I think I'm going to end this video here, and then we will do question number 7 in the next video, because it's getting already, it's 1 hour 12 minutes or so. So I'll end this video here. I'll see you in the next video.